ionic and molecular compounds. So first off, the general formula of all acids are going to follow this HX, where anything that starts with hydrogen and is bonded to either an anion, a negative ion, or a polyatomic, that's what we're going to use to identify that as an acid. So here A starts with hydrogen bonded to fluorine, acid. Starts with hydrogen bonded to the polyatomic nitrate, that's an acid. Starts with potassium, has hydroxide in it, has to be a base. Okay? And there's a little grid here that does a little summary of some of the basic patterns that we're going to see when it comes to naming formulas of an acid. And there's really three simple rules. The first thing we're going to do is identify the proper name for X. Okay, that alone tells us most of what we need to know to correctly name the acid, because the suffix, the ending of your negative ion, based on what that is, it follows this particular pattern. The second thing we're going to do is add the prefix hydro to anything that ends in ide. So add hydro to the start of all ides. And then the last step is to change the suffix based on, again, that ending of that particular negative ion. So anything that ends in IDE, which most ions end in IDE, like the chlorine ion, we call the chloride ion. That's the only time we're going to add hydro to the start of the name of the acid, and then put in the root or the stem of this name, and then it ends in ic. So if we had something like HCl, we would call that hydrochloric, and then always put the word acid at the end of the name for the acid. Okay? If we had something like SO3 negative 2, which is the sulfite ion, because it doesn't end in IDE, to categorize all the polyatomic acids from the rest, we don't put hydro. So these don't get hydro at all. And so if this was H2SO3, we would just take the stem of the sulfite ion, which is sulf, and we add OUS to it. So this is what we would call sulfurous acid. And then the only other suffix that polyatomics had was something ending in ate, like the nitrate ion, and that HNO3 ending in ate, again, no hydro, but we would take the stem of nitrate and end it in ic instead of OUS to indicate the different suffix. So this would be nitric acid. Okay, so there are three acids here. We're going to come back and name those, but we're going to very quickly talk about how we name bases, and then we're going to pause the video and practice those names to see how we do. The general formula for any base, M stands for any metal ion, so most of the periodic table, bonded to hydroxide. That's it. You see hydroxide, that we can identify point blank as a base. And naming bases is the same as naming an ionic compound. So if we had something like CaOH2, we see that it's got OH. We see that calcium's a metal, so we would say that that's calcium hydroxide. That's it. That's all we do to name it. There's no suffix changes. There's no prefix changes. So with that being said, I'd like you to pause the video, practice naming these four compounds, and then resume the video to see how well you do, and then we'll go into going backwards to go from formula name to the actual formula. All right, so for this first example, we've got HF. So the first thing we want to do is identify the proper name for X. X is whatever hydrogen is bonded to. So the F ion is a -1 charge. And because it's just the fluorine by itself, we call that the fluoride ion. So because F- is fluoride, we're going to follow that pattern for anything that ends in "ide." So this acid has to start with hydro, because all ides start with hydro, and then the stem of fluorine, so we'll say fluor, and then all the hydros end in ic, so hydrofluoric acid. Okay? NO3 up here was our nitrate ion, so that's an exact copy from this row up here. No hydro, the stem of nitrate is NITR or nite, and we're going to end that with ic. So this is just nitric acid. C is a curveball because there's no hydrogen at the start. It's not an acid, so this is a base. So we would identify the name of K, which is potassium, and then label that with hydroxide. So we just call that potassium hydroxide. And then the last one, we've got hydrogen, 2 of them because SO4, the sulfate ion, is a -2 charge. And so if this is sulfate, just like up here, anything that ends in ate doesn't have the hydro prefix and has to end in ic. So this being different than sulfite means that it's not sulfurous acid, but it's sulfur as the stem, and this one's going to end in ic because sulfate ends in ate. So we're going to call that sulfuric acid. Okay? So the key part to going backwards is we have a lot of clues within the names of our acids and our bases to figure out what is not having hydro here tell me about. Should it be an element by itself or a polyatomic? And then once we identify what that X should be, we can use its charge to determine the formula. Okay, so we'll do the first one as an example. We've got chromic acid. So there's no hydro and it ends in ic. Well, that's the pattern that we used for any nonmetal ion or polyatomic ion that ends in ate. So really what we are looking for is the chromate ion. And so if we go to our periodic table, and we identify chromate on the periodic table, that's CrO4 with a -2 charge. So this is really CrO4 -2 as the polyatomic in that acid. And because it's a -2 charge, the formula of the acid has to start with hydrogen, and we're going to have 2 of them to counteract that -2 charge because each hydrogen is +1. Okay? Here we've got iron 2 hydroxide, iron being a transition metal, so that means this is +2. Hydroxide is always a -1, so we would write 1 iron and 2 -1 hydroxides bonded to that. And then here we've got hydroiodic or hydroiodic acid. And so because we have that prefix hydro ending in ic, that means that that nonmetal root is by itself. There isn't a polyatomic involved. So iodine, being a halogen in group 7, means that as an ion, it's going to be a -1 charge. So we're going to have 1 positive hydrogen to bond to that 1 negative iodine. Lastly, lithium, located in group 1, is a +1 charge. Hydroxide, again, is a -1 charge, so lithium hydroxide has the formula of LiOH.